Hello everyone. Today, I will talk about a new method for understanding the behavior of image classifiers, which has been accepted at CVPR 2024. Our task is to identify important pixels for the classification model. Existing studies focus on the visual explanations of classifiers. You may be familiar with GradCam. GradCam explains the model's focus areas by visualizing them as heat maps. In many cases, the heat map often includes the class object. However, we found an important observation. Which of the following two pixel groups has a higher confidence score? Here, you might think that the model sees the duck part, which contains many class objects, would have a high confidence score. However, the confidence score is actually low. On the other hand, if models also see the background part, the confidence score is high. So we found that the model's prediction uses background information as well as a class object. So our result is that we propose a method for identifying an important group of pixels with high contributions to confidence scores. The name of our method is MOXIE. Theoretically, our method uses Shapley values and interactions. Previous work only used Shapley values, but we found that we also need interactions. Firstly, let me introduce the Shapley value and interaction. Roughly speaking, Shapley values measure the contributions of individual pixel on the model's input. We calculate the difference between the confidence score with pixel I included and without pixel I. Next, interactions measure the contributions of the cooperation between two pixels. In other words, it measures the synergy when two pixels are input together. Here, we want to know which group of pixels are important. In other words, we think about the problem of finding a subset that maximizes the confidence score. To solve this problem, we have proposed a method. Our method is a greedy algorithm. The best pixel index B_k is defined in this way. Our method uses Shapley value and interaction. The first term measures the individual contribution. The second term measures the joint contribution between already selected patches and new ones to append. Specifically, we first start with an empty image. Next, we select this patch because this patch has a high Shapley value. Next, we select this patch because this patch has high Shapley values and high interactions with the previously selected patch. In the same way, we select other patches. Next, we show the visualization. The highlighted image patches are selected based on their contributions calculated by each method. For the insertion, patches are selected greedily according to the scores until getting the correct classification. As you can see, MOXIE selects the least number of patches to classify correctly. Conversely, for the deletion, patches are deleted greedily according to the scores until the classification fails. Then, MOXIE deletes the least number of patches to fail classification. Next, we show the experimental result. In insertion and deletion curves, we analyze the change in classification accuracy on partially unmasked or masked images. The idea behind the insertion curve is that the model can successfully classify using only the important patches. The horizontal axis represents the unmasked image rate. Our method performs best when fewer patches are unmasked. Interestingly, with only 4% visible part of each image, our method achieves 90% accuracy, while GradCam and attention rollout achieve less than 5% accuracy. On the other hand, our method can also be optimized for the deletion curve. The results show that our method causes a sharp decrease in classification accuracy compared to the other methods. In short, our method can identify groups of pixels suited for both the patch insertion and patch deletion. This provides explanations for the model's decisions from a new perspective. If you'd like to hear more details, please visit our poster presentation. That is all. Thank you for listening.